Hey there. Hold on. I wasn't on the right speakers. Okay. I'm currently at the Jones Center again with a mask on my ear and cereal that I'm eating for a snack so that I can keep my mask off while I record a video. It's just kicks. I like kicks. All right. We are on solving systems of equations. And this is actually part 2. It's a very fluffy 2. Let's just jump on in. So let's think about why adding and subtracting equations works for solving systems of linear equations. Okay, if I begin, here's an equation. 50 plus 1 equals 51. Hold on, I have to grab something. I need my textbook because I'm going to move away from this screen. I still need to be able to read what it is that we're doing. So perform each of the following operations and answer these questions. What does the resulting equation look like? Is it still a true equation? Okay, so I need to move to here because I rewrote the equation so I could actually use it. So the first question was add 12 to each side of the equation. So if I just do a 50 plus 1 plus 12 equals 51 plus 12, that gives me 63 equals 63. So what does the resulting equation look like? So there's my equation. And is it true? Yes. I could also write it like this. Plus 12 and plus 12. And I'm still going to get the same answer. Right? Okay, let's try another one. Add 10 plus 2 to the left side of the equation and 12 to the right. So 50 plus 1 plus 10 plus 2 equals 51 plus 12. Okay, so if I look at the left side, that gives me 51, 61, 62, 63. And then this would be 63. So 63 equals 63. Okay, so still the same thing. And again, I could write this. Let me move my screen a little bit. 50 plus 1 plus 10 plus 2 equals 51 plus 12. You know, keeping my line down the middle. And it's still going to be 63 equals 63. Okay, that is true. All right, so it doesn't matter which way I write it, because if we look at this, 10 plus 2 is the same as 12. So I'm adding 10 plus 2 to the left and 12 to the right. They're the same, they just look different, right? All right, what's next? Add the equation 4 plus 3 equals 7. So here, 50 plus 1 equals 51. I'm adding 4 plus 3 to the left and 7 to the right. 4 plus 3 does equal 7, so they may look different, but they're the exact same thing. 4 plus 3 is equal to 7. 4 plus 3 is the same as 7. All of those things. So if I had this, I'm just going to go down. Like this gives me 4. That gives me 54. Add that together, I get 58. And here, I get 58. Okay, true statement. All right. Okay, so question 2 says, still eat my snack. Write a new equation that, when added up to 50 plus 1 equals 51, gives a sum that is also a true statement. So if I look, I could do, I don't know, write a new equation when added to 50 plus 51. Let's say, no, let's do 6 plus 4 equals 10. So that's an equation. So I'm doing plus 6 plus 4 equals 10. 56 plus 5 is 61 equals 61. Okay, that does work. Okay. Now it wants me to write a new equation that, when added to 50 plus 1 equals 51, gives a sum that's a false equation. I think I'd have to add something that's false. 50 plus 1 equals 51. If I added something like 3 plus 2 equals 7, I get 353. Oh, let's do it here. 53 plus 3 equals 58. 56 equals 58, which is not true. Nope. Okay, that doesn't work. All right, so why do you think the resulting equations remain true even after we add numbers or expressions that look different to each side? Okay, why do you think the resulting equations remain true even after we add numbers or expressions that look different to each side? They may look different, but they're actually the same. Okay, just because 4 plus 6 equals 10, which we used that one, just because those look different, they're actually the same. 4 plus 6 is 10, and 10 is equal to 10. So they're the same. Snack. Suppose we subtract 12 from the left side and subtract 5 plus 7 from the right side. Would the resulting equation still be true? Yes, because 5 plus 7 is equal to 12. Okay, because they are equal. It's still true. So we have 50 plus 1 equals 51. And we're going to subtract 12 from the left side and subtract 5 plus 7 from the right side. So on the left side, we get 51 minus 12, which is 50, 49, 39. And on the right side, we get 51 minus 5 plus 7. Okay, so 51 minus 5 minus 7 is 56. Nope. 46 minus 7, which is 39. So we got 39 on both the left side and the right side. It works out, right? So the resulting equation is still true, because it is, because we subtracted 12 and we subtracted 5 plus 7, and 5 plus 7 is equal to 12. All right, let's move on. That's not Kix, and it's stale. Oatmeal squares. All right, so here we are. A teacher purchased 20 calculators and 10 measuring tapes for her class and paid $495. You guys have learned how to write equations for this. You should be able to. If we said that was 20 times the cost of one calculator plus 10 times the cost of one measuring tape and spent $495. Okay, you guys know how to do that. Then she placed another order of 8 of the exact same calculators and 1 of the measuring tape and spent $178.50. So that would be 8 of the exact same calculator plus 1 of the same measuring tape and $178.50. This system represents the constraints of the situation. Constraints are the limits, how the equations are set up, how the system is set up. 20 calculators, 10 measuring tapes, $495. 8 more of the same calculator, 1 more of the same measuring tape, $178.50. Okay, that's the constraints in the situation. Other things we have to know is C represents cost of the calculator. M represents cost of the measuring tapes, right? So do they have to be whole numbers? No, they have to be real numbers. They can't be negative numbers. There's a lot of things that they have to be, but they do not have to be whole numbers. So, talking through this. So what does each equation represent in this situation? The first equation was the first time the teacher went shopping. She bought 20 calculators for some amount of money, 10 measuring tapes for some amount of money, and spent $495. The second equation is the second time she went shopping, okay, and how much she spent. If we are solving the system, what are we really looking for? I'm looking for if she spent that much money and bought those many items, what was the cost for one calculator? And what was the cost for one measuring tape? And it would be the cost that makes that system true. It's only one answer is going to work. One answer, one cost for calculator, one cost for measuring tape is going to make that system a true statement. All right? So solutions to the first equation mean anything that make just that one equation true. And let's go over here and look. If we did 20x plus 8y equals 495, snack. I feel a little guilty eating snack in front of you guys. Just a little. So this is the equation that represents her first shopping trip. Okay? So any ordered pair that's on this line makes this equation true. Okay, what you see right there, $15.87 for a calculator and $22.02 or $22.20 for measuring tape makes that equation true. Okay, we could go probably more realistic. No, this way. $21.80 for a calculator and $7 and I don't want to round. I don't want three decimal places. There we go. $21.75 for a calculator and $7.50 for measuring tape makes $495 true. Okay, so the solution to the first equation is any ordered pair on this line. Snack. What do solutions to the second equation mean? Let's look. I'm going to hide the first equation. The second equation was 8x plus 1y. You do not have to type in the 1. 178.50. What's this equation? Any ordered pair on this line makes just this second equation true. Any ordered pair on it. $20.22 for a calculator, $16.74 for a measuring tape. Just this equation true. Okay, now if we turn on both graphs, that ordered pair there, it would be nice if it weren't three decimals. I don't know. Oh, didn't mean to do that. Wrench. Yeah. I don't think I can change. That's okay. We know that we are going to have to round because we're in dollars and cents. But that ordered pair right there is the only solution that makes both equations true. And that's important. It's a system of equations where the graphs cross is where they're true. Right? So we said solutions to the second equation are any solutions that only make the second equation true. For each equation, how many possible solutions are there? For each separate equation, there are infinite solutions. Because not infinite, it's dollars and cents. So lots of options of dollars and cents that make each separate equation true. Now, the solution to the system is where they cross. And I've already turned off that page. Let's see if I can find it. Let's see. 1, 2. Find the solution to the system. Number 2. Sorry. So the calculators are $21.50 and the measuring tape is $6.50. Okay, so we solved it by graphing, not by substitution, and it was fine. So to be reimbursed for the cost of supplies, the teacher recorded items purchased: 28 calculators and 11 measuring tapes. Amount $673.50. All right, so write an equation to represent the relationships between the numbers of calculators and measuring tapes, the prices of those supplies, and the total amount spent. I'm going to come up here, change colors, and just do this magic. Just adding them together. 28C, I'm collecting like terms. 11M equals 13, 10, 17, 4, 5, 6. $673. Is that what they told us? Get back to the problem. $673.50. Yep, good job. Okay. How is the equation related to the first two equations? We just added them together. We added the first two equations together and got this equation. 28C plus 11M equals 673.50. In this situation, what do the solutions to this equation mean? Well, let's graph it. Watch this. 28x plus 11y equals 673.50. I think I get that wrong. 673.50. That red, and there we go. Our solution is the same, 2150 and 650. The solution is exactly the same, okay? Because the equations are equivalent. Okay, this first equation and the second equation and the third equation are all going to intersect at the same spot. Adding these two equations together for a third equation does not change anything. Okay, right there. Or, I can't see the, yeah, it's really awful. There's a mistake here. I'm so sorry, guys. I was wondering why that didn't look right. Gosh, I've been leading you astray all this time. Okay, 2150 and 650. Okay, the first and the third, and then the second and the third. 2150 and 650. So that was a mistake on my part. I typed something in wrong and just went with it. Sorry about that. Okay? All right, let's go back. So how many possible solutions does this equation have? Well, the equation all by itself has many, many solutions. They all have to be positive. They all have to, be dollars and cents. They have to be rational, etc. Okay, the first equation was 20C, 10M, 495. We added 8C plus M to the left and 178.50 to the right and got 28, 11, and 673.50. The two sides of the resulting equation still equal. Okay, yes, because we graphed it and it still gave us the same solution. Because we added them together and it didn't change anything, they're still equal. We proved that in our warm-up. I already did this. Predict what the graphs of all three equations would look like. Okay, that third graph, if we looked at it, right there, it's actually pretty cool. The green graph, which is the ones we added together, are right in between the red and the blue. That's not a mistake. It's pretty cool. They all have the same intersection, so they're all equal. The solutions to all three systems are the same as the solutions to those two, or those two, or those two. Okay, they're all equal. In this situation, why does it make sense for the graphs intersecting at the same point? What does that point mean? It's the solution to the system. Just because we added the first and the second equation together doesn't mean that the system changed any. It's still the same system. In general, why does it make sense for a third equation that does the sum of the two equations to share a common solution? Because the third equation looks different, but it's still the same. Okay, it's actually the same, it just looks different. Were you able to solve the system by adding or subtracting equations without graphing? Why or why not? Not easily. If we look, the two equations were this. We had 20C plus 10M equals 495, and 8C plus M equals 178.50, I think. Yeah. I don't have anything that is the same term, or any terms that have the same variables and different coefficients. Like my C's are 20 and 8. My M's are 10 and 1. Okay, they're not the same, so I can't just add them together to eliminate one of the terms. Now, I know what I want to do with this. I just don't want to jump the gun. Okay, and we're not going to jump the gun yet. But there is a way to do this. You just have to be patient, and we're going to get to it in a bit. All right, so let's try this. Solve each system of equations without graphing and show your reasoning, then check your solutions. So here, my first term is a 2x and a negative 2x. So I can add those together. 7y equals 21, y equals 3. Go ahead and plug it into anything. Just substitute it. 2x plus 9 equals 7. 2x equals negative 2. X equals negative 1. So I have 3 and negative 1. Let's go ahead and check. Negative 2 times x plus 3 times y equals, which one did I use? I used the second one, so I need to change something. This is a 4. I used the second equation. So this would be 2 plus 12 equals 14, and that is a true statement. Right here, if I add these together, this term's going to cancel because they're the same variable, same coefficient, different signs. So I get 5x equals 10, x equals 2. Go ahead and plug it into either equation. 2 times 2 plus 3y equals 7. 4 plus 3y equals 7. Subtract 4 from both sides. Y equals 1. So I have 2 and 1. Go ahead and substitute it back in to either equation. 2 times 2 plus 3 times 1 equals 7. I want to make sure I use the right equation. So 4 plus 3 does in fact equal 7. We're good. All right. At this point, I'd love for you guys to try these on your own, but we're recording, so I can't. Okay, what do I do here? I have the x's are the exact same variable, but the numbers are the exact same too. So I really need to change the sign of each term in that second equation just by multiplying it by a negative 1. So once I've multiplied by a negative 1, then I can go ahead and add, and it cancels out the 2x. Here, this gives me a negative y equals negative 4. So y equals 4. I'm already out of room. So we're going to go back. 2x plus 3 times 4 equals 5. 2x plus 12 equals 5. Oh, we're going to get a fraction. I don't want a fraction. Ugh, we are. Okay. 2x, if I subtract 12 from both sides, I get a negative 7. So x equals negative 7 halves. Okay? I just checked. It's right. Now this last one, I don't have any terms where I have the same variables, but the coefficients are the exact same. and either opposite signs or not. Okay, but I can actually multiply this whole equation by -3 and make it work. So -3 times 2x is -6x. -3 times 3y is -9y. 3 times 19 or 16 is 48. So -48. So I multiplied 3 by each term. Rewrite the second equation and add them together. And the x term cancels. So I have a -14y equals -48 plus 20 is a -28. Divide both sides by -14, y equals 2. Plug that back into any equation you see. 2x plus 3y equals 16. 2x plus 6 equals 16. 2x equals 10. X equals 5. Okay, there's our solutions. That last one was tricky. See how they got harder each time? The first one was easy. You think, yeah, I got this. The second one was a little bit harder. You're like, yeah, I got this. The third one's like, ooh, that's weird. And then the fourth one, oh, yeah. Don't stop watching. What happens if we add or subtract the equations? But nothing special, okay? Same stuff. Why were you able to solve the first 3 systems by elimination but not the last one? Okay, that last one, each term had different coefficients, different numbers in front of them. We still did it though. We made them have the same coefficients. What features were in the equations in those systems but not the last one? Okay, we always want the same variable, same number, different signs. That's what we're always going for. All right, it's a long video, I know. So here, I've got 2 terms with the same variable, same coefficient, different signs. We're good to go, okay? I'm gonna skirt through this. Well, I think we're good. We've really dug this one into the ground. All right, so now we're going to say, I can explain why adding or subtracting 2 equations that share a solution results in a new equation that also shares the same solution. All right, and we're not doing the cool down, but there's a vocabulary and more vocabulary and more vocabulary. All of this is in your topics section. Okay, nice work today.